We're going to start our session with a little bit of an introduction on the history of computer programming. And we'll start with binary instructions. Binary instructions are just the ones and zeros that actually allow a computer to talk to whatever devices it needs to talk with. And as you might guess, binary instructions are rather slow, but it is the first way that computer programming was done. In fact, when I first started programming, we actually hardwired with wires an IBM 360, and it was all done in binary. As you might guess, binary instruction cases are very, very error-prone. One bit out of place and nothing works. Because of that, development was also slow, and any time that you find slow development, of course, costs soar. So there was always this search to look for a better way of writing computer programs. Another issue that quickly manifested itself in the early binary days was programs were very, very difficult to debug. You had to be an expert in binary interpretation of data, generally meant understanding the hexadecimal numbering system, and there were all other kinds of issues that made it very, very difficult to work with the binary instruction set. So this first generation of languages, the binary languages, were quickly replaced with assembly language. Now, assembly language used mnemonics or abbreviations for the instruction set. So instead of having C9 meaning return, they actually used the word RET, R-E-T, as a mnemonic for the return instruction set, which was a great improvement over looking at something and seeing a hex C9 and trying to remember what that meant. So assembly language quickly replaced binary instructions as the way of writing computer programs. These languages, there's various types of assembly language. They're all very specific to the microprocessor or the mainframe CPU for which they are written, but they're all called second-generation languages. But they, too, are very error-prone. It's still difficult to look at abbreviations and feel comfortable with understanding exactly what the logic flow is for the program. Development still remains slow, although it was a quantum leap above binary. By today's standards, the programs are still fairly slow, and because they're slow, program development is very expensive. Again, debugging with assembly language is an art, and simply starting a program and trying to walk through it in a single step and understand the assembly language is not an easy process. So we still continue to evolve, and we go to high-level languages. Because of these problems with the second-generation languages, we eventually evolved into the high-level languages. And Fortran and COBOL were the first two to gain any widespread acceptance in the programming community. These were a quantum leap above the first two generations. Much less error-prone, and because the languages themselves were less error-prone, you got faster development times, which made costs drop, which made programming less expensive. Most of the programs were much easier to debug because you were looking at almost English-like words rather than mnemonics or actual hex numbers. So these third-level languages, or third-generation languages, were a quantum leap above other languages. But still, the fact remained that of the development time and the development costs for software, even using third-generation programming languages, it still was about a 20%, 80% split between writing the code and debugging the code. In other words, 4-to-1 spending time debugging the code that was already written. So writing programs actually with third-generation languages was much more efficient, but still error-prone. One of the problems that caused the widespread debugging issues was that data in these third-generation languages all had global scope. What that means is that any variable declared at any point in the program could be used in any other part of the program. And it was very easy, for example, if you were doing a loop counter, to use a variable, say, like I, like we always do in programming, and march it into a loop and forget that some other program was using that same name for some other purpose at some other point in the program. So these collisions with data that had global scope was a source of program errors, and it was very difficult to track those because you couldn't be sure where in this monolithic program the two were colliding. Because of this, there was another attempt to go into the fourth generation languages, and these were founded on structured programming principles. C, Pascal, BASIC, and there's a whole other family of languages that cropped up at this time that were built upon structured programming principles. C was one of the languages that really found a firm footing. And I think the reason was because it was a crisp, small language in the sense that it only had 24 keywords. It had no I/O provided for it, so you didn't have to learn that really. And all of the I/O commands and all of the other features of the language were not built into the language, but were rather callable from library routines. And this made it possible to write your own and substitute them for the base language provisions. Made the languages very flexible, very extensible, and it made them suitable for almost any specific purpose that you might have. So structured programming was a paradigm that came in and was well embraced by the programming community at a very rapid pace. One of the features of structured programming is the concept of subroutines. Now, Pascal and COBOL, the third generation languages, embraced that concept, but they weren't there at the very beginning. Subroutines came in at a later stage in those languages. And the idea was that it was possible to go to a small routine and have that routine perform a specific task and return a value to the main sequence of the program. Because of this, subroutines allowed some isolation away from the global scope data. And this was a good thing. Most of the subroutines at that time had data that when you entered the subroutine, those variables came to life, and when you left the subroutine, those variables died. And that made collisions in other parts of the program less likely. Another feature of structured programming is that we get data typing for the first time. In many languages, and for example, the early versions of BASIC, you declared a variable. In fact, you didn't even have to declare it. It came into life as soon as you used it, and they were all the same type. They were essentially floating point numbers. The exception would be string data, but it could sense how you were going to use it, and it created it. But the typing, which came in with particularly C and Pascal in those languages, meant that you had to define the variable before you used it. This was a great enhancement to the languages because it allowed you to check the type of the data, and it prevented data collisions as well. You also got improved tools for programmers coming in at this time. Integrated development environments, or IDEs, combined the text editor with the assembler, with the linker, with the librarian. So in one particular program or one executable, you had all of those tools which used to be separate steps in the earlier development days. Debuggers were also integrated into the IDE, which made it very easy to test a program. You could do fast iterations. In my first programming experience, which was on an IBM 360 mainframe, I was a lowly graduate student, so I would have those punched cards. I would walk it over to another building. I would pass it into this window, this hand. I never saw the person. I just saw this person grab the deck, and I would get a number in return. And I would continually call that number until that particular process had been done, only to find out that I had a 1 comma wrong on card 128. And you'd go back, fix that one card, and submit the deck again. That caused you to look at a deck of cards, of programming cards, and it caused you to debug the programs in your brain. Today's IDEs with the debugger in them causes students to do the trial and error. I'll fix this until it works, and not necessarily understand what they fix. So IDEs, I think, are some kind of a mixed blessing because it gets people to be lazy. And that's not necessarily a good thing, but it does speed up the development process. Other tools, profilers check the performance, looks for bottlenecks in a program where you're spending too much time, and looking for ways that you might improve the performance of the program. The other thing that we're starting to see with structured programming languages is the concept of scoped data. Instead of having global scope where a variable is visible throughout the entire program, in these structured programming languages, each subroutine has a set of data that comes into existence, and when that subroutine is exited, those pieces of data cease to exist. This results in several things, the biggest being data collisions are much less likely. Secondly, it's pretty easy to see where the data is going wrong because of its life. You can now look where it's in scope, and you know that it's localized probably to that one specific subroutine. And the other advantage of scope data is it's less resource intensive. Because these data die when the subroutine or their use is exited, those resources can be freed up for other uses in the program. Now, object-oriented programming. It too is an attempt to solve some of the issues that have existed with 1, 2, 3, and now 4th generation programming languages. The idea that we still spend 20% writing a program and 80% debugging it still remains true, even though we've made monumental jumps in the way that programs are written. It still is not an exact science. Most people think that object-oriented programming started with C++ back in the early 1980s. That's really actually not true. It started in the early 60s with a language called Simula. And what these guys were trying to do, they were doing a project, I believe it was for Otis Elevator, and they were trying to model the arrival of people at an elevator and pressing the button for the elevator and trying to simulate how the elevator should respond to those button presses. And they were trying to design a hospital elevator system. And the problem was they realized that every time somebody arrived at the elevator, they had to write, in essence, another program to cope with that person. And somebody said, well, wouldn't it be nice if we could just create a person object telling me that that person has arrived at the elevator, leave the main part of the program alone, and just deal with the fact that there's another person there. So this gave the entire concept of objects a birth back in the 1960s. C with classes was developed by Bjorn Stolstrup back in the early 1980s, and I was fortunate enough to hear one of his early presentations at the Software Development Conference in San Francisco. And he was the keynote speaker. There were about 750 of us in the audience. And Bjorn is an extremely bright person, works at Bell Labs. I think he still works at Bell Labs. And was doing a lot with C. He was on the C ANSI committee, and he started developing this C with classes with an eye to what Simula was trying to develop and solve 20 years before. Anyway, he gave this presentation, and we walked out afterwards, and all 750 of us said, what the hell was that all about? None of us really had the penny drop. We did not understand the concept of what objects were. So that's really the starting point where we have to concentrate our first efforts on understanding what object-oriented programming is all about. C# was introduced around 2000 by Microsoft, and it is Microsoft's answer to Java. Microsoft's not going to admit that anybody developed a language that's better than something it developed. So Java gained popularity in good measure because of the World Wide Web, and Microsoft wanted to respond with some language that offered the same features as Java, but perhaps a better or simpler development environment. Why use object-oriented programming? If you take and summarize all of the issues that we talked about in the last, 10 or 15 minutes, all of them are centered on trying to lower the cost of program development. And it's felt, and I think rightly so, that object-oriented programming brings an awful lot to the table. One of the three major points of object-oriented programming, and indeed it's called the object-oriented programming trilogy. The first one is encapsulation. The idea of encapsulation is that you hide the data. You keep one part of the program that has no business knowing about a piece of data away from the section that needs to know about that piece of data. The concept is not new. It's the same thing that kings used to do when they hid the princess in the tower. They were trying to keep her away from the commoners. Well, it's the same thing in programming. If you can hide your data so that nothing can mess around with it, the chances of contaminating or having side effects with that data are enhanced. And that is one of the major areas where bugs creep in, is where one piece of a program can manipulate inadvertently another piece of data in another section. As you'll see shortly, object-oriented programming is designed to encapsulate the data, to isolate it from the rest of the program. The second leg of the trilogy is called inheritance. Inheritance, simply stated, is the ability to stand on the shoulders of someone else. The idea is that if I've written this piece of software once, there's no sense to write it again if I do it in the right way. If I do it in a flexible and extensible manner, I can reuse that software. Inheritance then builds upon the concept of code reuse, and it also builds upon the concept of looking for commonalities in the data, isolating those common parts, and simply creating new objects that can draw upon that common interface if it needs to do so. The third part of the trilogy is the concept of polymorphism, which in the Greek translation simply means many shapes or many forms. But really what it means in an object-oriented programming sense is that a program can respond to an event, like a Windows programming event, such as a button click or something like that, in many different ways. We can send one message to a class, and we can let that class decide how that specific message should be handled, even though there may be multiple different objects based on that particular message or receiving that particular message.